Okay, welcome to Day 2, Part 1. Here we're going to take a look at graphs, of which the singly linked list and binary search tree that we looked at in Day 1 are just two particular examples. We're going to take a look at more general graphs than that. We're also going to discuss the breadth-first search algorithm that you can use, to find the shortest path between any two nodes in a graph. So, a graph is simply a collection of vertices connected by edges. The binary tree obviously is an example of a graph. A road map is an example of a graph showing cities and towns and connections between cities and towns. You can have a graph representing a social network, a graph representing friendships among officers of corporations, all manner of graphs. Some graphs are undirected, that is, they specify a commutative relationship. You might have a friend who has you as a friend, so that's not a directed kind of relationship. Other graphs are directed. For example, a manager is at a higher level in the corporate hierarchy than an employee. So employees report to managers, and that's a directed kind of relationship. There are also both unweighted and weighted graphs. If we have a graph representing friends in a social network, we could say things like A knows B, B knows A, or we could measure the weight of the connection between two entities. In other words, if A sends 1,000 emails to B, but only sends 5 emails to C, then we could say that A is 200 times as connected to B as A is connected to C. There are many ways of representing a graph in code. One way is to use something called an adjacency list, and Guido van Rossum, the BDFL for Python, suggests using a dict to keep track of which nodes are connected to which other nodes. Here's an example of a graph here on slide 4. Perhaps this is a social network of people who know each other. The graph G describing this social network has each entity in the social network as a key, and then associated with each entity is a list of the people that that entity is associated with or connected to. So A is connected to B, A is connected to D, A is connected to F. B, on the other hand, is connected to A and to D. C is only connected to D, and so forth. So this dict represents all of the items and all of the connection between the items in this social network. Now, here on slide 6, we have a much larger network. Let's suppose that this represents connections among people in some profession. Me is here, Ed is over here, and I would like to be introduced to Ed. Now, as opposed to just randomly walking up to Ed and introducing myself, I'd prefer to be introduced to Ed by one of Ed's friends. Well, I have friends, my friends have friends, my friends' friends have friends, etc. Hopefully, there is some connection from friend to friend to friend in this network that will eventually get me to Ed. And what I'd like to be able to do is to find the shortest path from me to Ed in this network. Now, this assumes that such a path exists. It's possible that as we traverse out through the friends of friends of friends, that I might never reach Ed that way, but we'll hope that that's not the case. Okay, so the breadth-first search algorithm is an algorithm that will identify for me the shortest path from me to Ed. What we're going to do is we're going to build a tree where me is the root of the tree, and then one level below me is going to be the people that I am directly friends with. Below that will be, for each friend of mine, their friends. other than me. We're not going to come back up to me. And so on. And we'll keep building this tree downward and downward until eventually one of the branches of this tree comes to Ed. And at that point, our algorithm is over, and we will have discovered the shortest path between me and Ed. So, diagrammatically, these red people are the direct friends of me. And if I then go one more step and add their friends, I add these green people into the network. One more step adds these purple people and then the yellow people, and you can see here that one of these is directly connected to Ed. So it takes me 5 steps going through this hierarchy of friends to get to Ed, and at that point I've done. I have found my shortest path. All right, so let's put this into code, more or less. We're going to look at some pseudocode here. First, we're going to have a dictionary, G, which represents this entire graph, and we know how to do that. Then we're going to have T, the tree starting from me and working outward from me. Now, once we have visited someone in this network, there's no point in revisiting that same person again. So we're going to keep track of a set of nodes that are already in the tree. What do I mean by this? Well, me is the root of the tree. A is one step below me in the tree. Then B is one step below A, therefore 2 steps below me in the tree. I could then say, well, B is connected to A, so A could go into the tree 1 step below B, but I've already visited A. A is only 1 step from me, and it's not useful to me. In fact, it's counterproductive to me to know that A is also 3 steps from me. In other words, if I go from me to A to B to A, I can find a path from me to A in 3 steps. But that's a longer path than the shortest path to A that I already know. So once I have found the shortest path from me to a particular node, I don't want my algorithm to explode exponentially by identifying longer paths as well. The fourth data structure that I'm going to need here is a list of nodes that are currently at the bottom of the tree, because these are the nodes whose neighbors I need to check next to go down to the next level of the tree. So here on slide 13 is my almost Python code for implementing this breadth-first search algorithm. And I've backed up the image over on slide 6 to the original image with no nodes identified yet as being in the tree. All right, so this is our breadth-first search algorithm. G, the dictionary representing the graph, is our first argument. Root, which is the argument representing the original item, is the second argument, and the target that we want to get to is the third argument. So in this case, in this example, root is me, target is Ed. Now, clearly the first thing in the tree is going to be root. So our set of items that we have visited, which starts out as empty, is going to have root added as its first element. And our tree is going to have root added as the topmost item in the tree. Each item in the tree must have a parent. In our case, none is going to be the parent of me, the root node. Our queue, or list, of items that are now at the bottom of the tree is just the root. Now, as long as there are items at the bottom of the tree, what we're going to do is we're going to grab the front item from that queue, and if that node that we've just grabbed from the queue is the target, that is, in this particular case, if the root is Ed, we're done, and we just return the path of items from me to Ed. Of course, me is not Ed, so what we need to do is drop down to this loop and say, okay, for the list of items that me is connected to, and remember in the dictionary, I use the item as a key, and what I get back from that is a list of the items that are directly connected to that item. So what I'm getting here is a list of items that are directly connected to me. If the current item is not already in the set of items that we visited, we'll add it to the set of items that we visited, and we'll add this item to the tree with the current node as the parent. Okay, now when I originally created the tree, the root node has no parent, so I specified none as the parent for the root. Here I'm specifying me as the parent for the node that is directly connected to me. That node that I've just added to the tree is now at the bottom of the tree, and so I'm going to append that node to my queue of nodes that are at the bottom of the tree. All right, so initially, using me as the current node, I'm going to get back a list containing A, I, and N, the three nodes that are directly connected to me. So for each value in A, I, N, I'm going to check if A is not in the set that I've visited, add A, and then add A as a child of me, and then add A to the queue of nodes that are at the bottom of the tree. Then do the same for I. Since I is not yet in the set of nodes that I visited, we'll add I to our set that we have visited now. We'll add I as a child of me, and we'll add I as an item at the bottom of the tree. And then finally, N is not in the set that we have visited so far. So we add N to that set, we add N to the bottom of the tree, and we add N to our queue. At this point, now that I have looped through the items that are directly connected to me, the queue has been updated to contain A, I, and N. All right, so whereas root was the only item in queue initially, now that I've gone through and identified the items that are directly connected to me and added those as children of me, the queue has been updated to contain that list of children. So I'll go back up to my while loop, and sure enough, the queue of bottommost nodes is not empty. So I'm going to pop the frontmost item from the queue, which is A. And since A is not Ed, I go down and look for A's direct neighbors. Now, one of A's direct neighbors is B, and the other of A's direct neighbors is me. As I loop through B and me, B is not one of the items I've already visited, so I'm going to add B to the set of such items, and then I'm going to add B as a child of A. And I'll add B as a bottom item in the tree now. But the second time through the loop, me is in S, so I'm not going to add me again. The upshot is that B has been added as a child of A, and B has been added to the queue of nodes whose direct neighbors I need to check next. All right, so that's A's direct neighbors. The next value that we pop from the queue is I. I is not Ed, so we get I's direct neighbors from the graph. I's direct neighbors are me. Me is already in the set that I visited, so I don't do anything. And Q. Q is not in the set of nodes that I have visited, so I'm going to add Q to that set. I'm going to add Q as a child of I, and I add Q, the node Q, to the end of my queue of nodes that I still have to visit. And this just keeps going, crawling its way through this network, methodically working outward from me in rings of steps. I get all the one-step neighbors, all the two-step neighbors, and so on. And eventually I find Ed. All right, so having defined this BFS function, here is how I would call the BFS function. First of all, I have to define my graph dictionary. We'll assume that we've done that. And I pass in me as the root and ed as the eventual target. Okay, so to start things out, I add me to the set of nodes that I visited. I add me to the tree with none as me's root, although I'm not going to bother showing none here. And the queue of nodes that are at the bottom of the tree here, level 0, we're starting at the root of the tree, is just root itself. Then we go down and identify the direct neighbors of me. A, I, N, and oops, I forgot to notice V, but fortunately my code is smarter than I am, so my code will recognize V. Those get added to the set of nodes that I visited, and those get added into the queue of nodes whose neighbors I need to visit. Well, once again, my code discovers that I made a mistake in identifying A's direct neighbors. Not only is B a direct neighbor and me a direct neighbor of A, but J is also a direct neighbor of A. The only new direct neighbors of A are B and J, so those become the children of A. The only new direct neighbor of I is Q. It turns out that N and V do not have any new direct neighbors, because N's only direct neighbors are me and V, and both me and V are already in S, the set of nodes that I've already looked at. Analogously, V's only direct neighbors are N and me, and N and me are already in S, so V does not contribute any new neighbors either. Okay, so we've gone through step 1, identifying A, I, N, and V, and now we've gone through step 2, identifying B, J, and Q. B, J, and Q have been added at the bottom of our tree, and B, J, and Q have been added to S, the nodes that I visited. B, J, and Q are now the elements in Q whose direct neighbors I need to visit. In the third step, I will find these purple items. J has 3 new direct neighbors, E, L, and W. Q has 2 new direct neighbors, X and Y. These 5 nodes are added to the set S of nodes that I visited and become the elements in the queue of nodes whose neighbors I need to visit. In step 4, we discover these yellow items and add those into S, and they become the items in the queue. And then finally, in step 5, the new direct neighbors that we're able to find are M, G, and Ed. Because one of these is Ed, I'm now done. I have found the shortest path through this tree from me to Ed. All right, so these 3 nodes, M, G, and Ed, are added to the set of nodes that I visited, and they become the queue of nodes whose neighbors I would have to visit, except that I'll discover I've already found Ed, so I'm basically done. Here on slide 24 is the tree from me through 1, 2, 3, 4, 5 steps away from me. Starting from Ed, I can trace back Ed's parent, Ed's parent's parent, etc., to discover the shortest path from Ed back to me, which in turn is the shortest path from me to Ed. I would just reverse the direction of those references. All right, so I have found my target, and now I have the shortest path from me to Ed. If I continue for another step, I will discover 2 more new nodes, R and T, but that's the end of the road. If I put R and T into my queue and investigate the direct neighbors of R and T, I discover that the direct neighbors of R is Ed and of T is M, but those are already in my set of nodes that I visited, so I can't go any further. That's as far out as I can go, starting from me in this graph. You'll notice that there are 6 nodes, C, D, H, O, P, and U, that we never visited starting from me. All right, and I've highlighted those here on slide 26 in yellow. It turns out that these are connected to each other, but not to the network that contains me and Ed. Okay, so C is connected to D, is connected to O, is connected to H, U, P. They make up a separate so-called connected component within this graph. A connected component in a graph is simply a subset of nodes that are eventually connected to each other through some sequence of steps. And it turns out that this particular graph has 2 connected components. Okay, so it's not going to be possible to find any path from me to any of the nodes in the yellow connected component. Likewise, it's not going to be possible to find any path from C to any node in the white connected component. So the primary thing that the breadth-first search algorithm is usually used for is to find the shortest path between 2 items in a graph. Another thing that you can use breadth-first search for, though, is to identify all of the connected components that exist within a graph. Let's suppose that identifying connected components was our task, rather than finding the shortest path from me to Ed. Well, in that case, I could start with my graph, and I could simply look at the first item in the graph, A in this case, and I can use breadth-first search to identify the connected component containing A. Once I've found the connected component containing A, I could simply move on to the next item, B, and identify the connected component containing B. Well, B, I would immediately discover, is already in the set of items containing A. So I'm done with B. Then I would go on to the next item, which is C, and I would use breadth-first search to identify the connected component containing C, which would give me this yellow connected component. At that point, I would discover that I have all of the items in my graph in some connected component. And so I would know that I have identified all of the connected components, and there are actually just 2 of them. In a really large social network graph, containing hundreds, perhaps thousands or tens of thousands of items, what you typically discover is that there are a small number of really huge connected components, and then a much larger number of really small connected components with 1 or 2 or 3 items in them. Okay, so that's our discussion of graphs and breadth-first search enabling us to find shortest paths and connected components.